15 billion miles from Earth, NASA's oldest surviving spacecraft just ran straight into something scientists never expected to find. A wall of plasma so hot it reaches nearly 50,000 Kelvin, sitting right at the edge of our entire solar system. NASA has now confirmed it, and the data is genuinely unsettling. This isn't science fiction. This is real telemetry, sent back across billions of miles by a machine that's been flying since 1977, and what it found out there is rewriting everything we thought we understood about the border between our solar system and the rest of the galaxy. Let's start with the basics, because you need to understand exactly what these spacecraft are and where they actually are right now. Voyager 1 and Voyager 2 are twin probes launched by NASA in the summer of 1977, originally designed for a 5-year mission to fly past Jupiter and Saturn. That was the plan. Take some photos, gather some data, wrap it up. Nearly 50 years later, both spacecraft are still flying, still transmitting, and still pushing into territory that no human-made object has ever touched before. Voyager 1 became the first spacecraft in history to cross into interstellar space back in 2012. Voyager 2 followed in 2018. Both are now traveling through the space between stars, completely beyond the protective bubble our sun creates around the solar system. That bubble is called the Heliosphere, and it's basically a massive shield made of solar wind, a constant stream of charged particles blasting outward from the sun in every direction. This shield extends far beyond the orbit of Pluto, and it protects everything inside it, including Earth, from the harsher radiation that exists in deep interstellar space. For decades, scientists assumed the edge of this bubble, called the Heliopause, would be a relatively smooth, gradual transition, like slowly walking out of a warm house into a cool evening. What Voyager actually found at that boundary was nothing like that at all. To really appreciate how significant this discovery is, you have to understand just how little we knew about this region before these two spacecraft got there. Every previous model of the Heliosphere's edge was built using indirect observations from Earth, telescopes, computer simulations, and educated guesswork based on how other stars in the galaxy seem to interact with the interstellar medium around them. Nobody had ever placed an actual instrument out there to measure it directly. It would be like trying to describe the exact temperature of the ocean floor using only satellite photos of the surface. You can build a reasonable model, but you don't really know until something goes down there and takes the actual measurement. Instead of a gentle fade, both spacecraft recorded sudden, dramatic shifts in particle density and magnetic field strength right at the edge of the heliosphere. It wasn't gradual, it was abrupt, almost like physically stepping over a threshold into a completely different environment. Within that threshold, instruments on both Voyager probes detected something scientists have since nicknamed the Wall of Fire, an intensely energized region where the solar wind collides violently with the interstellar medium pressing in from outside. Here's where it gets genuinely wild. Temperatures within this boundary layer spike to somewhere between 30,000 and 50,000 Kelvin. To put that in perspective, that's hotter than the surface of many stars. We're talking about temperatures that would instantly vaporize any physical spacecraft if this were a dense environment. But here's the strange twist that makes this discovery both terrifying and completely survivable at the same time. The particle density out there is so incredibly low, so close to a true vacuum, that despite these extreme temperatures, there's essentially nothing for that heat to transfer into. Voyager doesn't get cooked because there simply aren't enough particles colliding with it to transfer that thermal energy in any meaningful way. Scientists explain this heat isn't coming from flames or combustion in any traditional sense. It's coming from charged particles moving at absolutely extreme velocities, colliding with each other and with magnetic field lines in a process called magnetic reconnection. That's when the sun's magnetic field lines and the interstellar magnetic field lines snap, twist, and realign, releasing sudden bursts of energy in the process. It's the same basic mechanism that powers solar flares back near the sun, except this is happening at the very edge of our entire solar system, in a region humanity had never directly sampled until these two aging probes flew straight through it. Magnetic reconnection is one of those concepts that sounds abstract until you picture it properly. Imagine two enormous rubber bands, each representing a magnetic field, being stretched toward each other from opposite directions. When they finally meet and snap together, all that stored tension has to go somewhere, and it gets released explosively as heat and kinetic energy. Out at the Heliopause, this isn't a rare isolated event either. The data suggests it's happening repeatedly, an ongoing tug of war between our sun's magnetic influence and the magnetic fields that exist naturally throughout the wider galaxy. Every time these fields clash and reconnect, they generate another pulse of that extraordinary heat Voyager's instruments picked up. And that tension between magnetic fields tells us something else, something that's honestly reshaping how researchers think about our place in the galaxy. The data suggests that the interstellar magnetic field pressing in from outside may be significantly stronger than anyone previously modeled. Picture the heliosphere like a giant balloon held up by the outward pressure of solar wind from within. If the pressure pushing back from outside is stronger than expected, that balloon isn't just floating freely through space. It's being actively squeezed, warped, and shaped by forces from beyond our solar system that we're only just now beginning to measure directly. Both spacecraft also detected something researchers weren't fully prepared for, a noticeable increase in plasma density both approaching and beyond the Heliopause boundary. This spike in density suggests compression happening on both sides of that transition zone, almost like two competing pressure systems slamming against each other along an invisible seam in space. The far more violent and far less understood than the smooth, quiet boundary scientists originally pictured decades ago. If you're new here, this channel breaks down the strangest confirmed discoveries from deep space missions, so go ahead and hit that subscribe button so you don't miss the next one. Now let's talk about what this actually means, because the implications here go way beyond just an interesting data point. For nearly 50 years, our entire understanding of the Heliosphere's boundary was built almost entirely on theoretical models and indirect observation. We simply didn't have a way to directly sample this specific region of space, because nothing we'd ever built had physically reached it before. Voyager 1 and Voyager 2 changed that completely, and what they found suggests our models were, in some very real ways, incomplete. This matters for reasons that go far beyond pure curiosity too. Understanding exactly how strong the interstellar magnetic field is, and exactly how it presses against our solar system's protective bubble, directly affects how well we can predict future changes to that boundary. If interstellar pressure really is stronger than previously calculated, that could mean the heliosphere itself is smaller, more compressed, or more vulnerable to shifting over long timescales than earlier models suggested. And since that bubble plays a direct role in shielding our entire solar system from harsher cosmic radiation, any changes to its shape or strength could eventually have consequences that ripple all the way back to Earth. The interstellar medium itself, the material that exists in the vast emptiness between star systems, turns out to be far more turbulent and far more energetic than researchers assumed. There's also the matter of a strange, persistent humming detected within this data. A faint but steady plasma wave signal that continues almost constantly, rather than only appearing during brief, dramatic events. Scientists believe this quiet hum may actually be some form of low-level plasma oscillation, a kind of background noise from interstellar space itself, something that had simply never been detected before because nothing had ever traveled far enough to listen for it. What's remarkable is how researchers even found this humming signal in the first place. It's incredibly faint, buried deep within instrument readings that were never specifically designed to search for it. Voyager's plasma wave instrument was originally built to detect the aftermath of large solar eruptions slamming into the interstellar medium, dramatic, obvious events. Instead, scientists studying years of accumulated data noticed something subtler hiding underneath those bigger signals, a narrow, persistent frequency that simply never stopped, quietly present in the background the entire time. It's essentially interstellar space, humming a continuous, nearly silent note, one that nobody was even listening for until they went back through the archives and found it. Think about the sheer scale of patience required to even collect this kind of data in the first place. These spacecraft are so far away that a single radio signal traveling at the speed of light takes over 20 hours just to reach Earth from where they currently are. Every single reading, every data point about temperature spikes or magnetic field shifts had to cross that entire distance before anyone on this planet could even begin analyzing it. And once the data does arrive, researchers back at NASA's JET propulsion laboratory have to piece together readings from instruments that are themselves nearly 50 years old, running on computer systems with a tiny fraction of the processing power inside your phone. That's honestly one of the most jaw-dropping parts of this entire story. Voyager 1 is currently operating with about 69 kilobytes of onboard memory. To give you some sense of scale, that's roughly the size of a single small image file today. The spacecraft still runs code written in the programming language Fortran, decades before most of the engineers currently monitoring it were even born. And despite all of that, despite the ancient hardware and the fading power supply, this machine is still out there, still functioning, still delivering revolutionary data from a region of space no human artifact has ever physically explored before. There's an important safety note buried in all of this too, something that genuinely matters for the future of deep space exploration. NASA has confirmed that despite these extreme recorded temperatures, the near-vacuum conditions at the Heliopause mean any future spacecraft passing through this region wouldn't face any real thermal danger. The heat exists, but the density required to transfer that heat into a physical object simply isn't there. This matters enormously for scientists already dreaming about future interstellar probes, missions specifically designed to study this boundary in far greater detail than these accidental pioneers ever could. But there's also a sobering reality hanging over all of this excitement. Both Voyager spacecraft are running out of power. Their nuclear generators lose a small amount of output every single year, and there's no way to refuel them out here, 15 billion miles from the nearest engineer. NASA has already been forced to shut down instrument after instrument just to keep these probes breathing a little longer. At some point, probably within the next few years, there simply won't be enough power left to keep any instruments running at all, and the flow of data from this completely unexplored region of space will finally stop for good. Engineers back at Mission Control already know exactly what's coming, and they've been preparing for it for years. Every instrument shutdown is a carefully calculated trade-off, weighing which piece of scientific equipment provides the most valuable ongoing data against how much power it consumes. Some tools have already gone dark forever, sacrificed to keep the core communication systems alive just a little longer. It's a slow, deliberate goodbye, stretched out over years rather than happening all at once, giving scientists every possible chance to squeeze out one more discovery before the silence finally becomes permanent. So think about what we're really witnessing here. Two machines built during the disco era, using less computing power than a basic calculator, are currently sending back some of the most important astrophysical data humanity has ever collected. Discoveries so unexpected that scientists are actively rewriting models about the structure of our entire solar system's boundary. It's a genuinely wild moment in the history of space exploration. And it's happening right now, not in some distant future mission, but through machines that have already been flying for nearly half a century. There's also something worth sitting with here, beyond just the science itself. When engineers designed Voyager 1 and Voyager 2 back in the 1970s, interstellar space wasn't even the primary mission. It was, at best, an ambitious stretch goal, something the team hoped might be possible if the spacecraft happened to survive long enough. Nobody could have guessed that these probes would still be operational decades later, let alone that they'd end up directly discovering a violently energetic boundary layer that completely upends prior assumptions about how our solar system interacts with the rest of the galaxy. Sometimes, the biggest discoveries in science don't come from a mission specifically designed to find them. They come from machines simply built well, enough and stubborn enough to keep going long after everyone expected them to stop. And that's really the heart of why this story keeps resurfacing. Every time NASA releases new analysis from this data, it's not just about plasma temperatures or magnetic field strength, even though those numbers alone are genuinely remarkable. It's about the fact that humanity's furthest reaching physical objects are still, after nearly 50 years, teaching us things we never expected to learn about the true edge of our cosmic neighborhood. If this story caught you off guard even a little, make sure to like this video and subscribe, because there's a lot more genuinely mind-bending confirmed space discoveries coming, and you will not want to miss a single one of them.